Yeah, so I think the audience number has already reached around 66 to 70. Maybe we can start. It is already 7:05.
Sure, I think we should start. So,
Yeah. Good evening, everyone. Hope you all are doing well in this difficult scenario. Today we are going to have a talk on inflation, quantum fluctuations, and primordial black holes. The speaker is a senior research fellow at IUCAA Pune, who also happens to be an alumnus of NISER from batch 8. Wonderful orator, and he has already presented several talks as alumnus of NISER at NISER and even at even many places outside NISER. Along with such a suave speaker, we also have an exciting topic to venture into, involving some of the terms which we don't really understand well, but yet keep coming across every now and then in pop sci or other references or in academia. The terms involving black holes and quantums. So and let's see how this talk goes. And without further ado, let's get started with this beautiful talk that awaits us.
hello everyone. I hope my slides are visible. Could somebody confirm if you can see my slide?
Yes, the slides are visible and you are audible.
Fantastic. So there's going to be a little. So say.
All the people are requested to keep their microphone switched off unless required to avoid any background noise.
Akshay, are you recording this?
Yes, Bhaiya. Someone among us has been asked to record this.
So I would request to stop recording when I end my talk. Okay, let the discussions not go into recording part, if that's fine.
Okay, Bhaiya.
Great. Super. This is going to be a complicated topic, and I think I'm going to talk roughly about 55 minutes. But depending on how it goes, I may have to push for 5 more minutes. So I request all of you to kindly have patience. And it's a little hard to give a talk online on such a complicated topic. So I had to like think about how I'm going to introduce different concepts of physics here. So I would request to have your questions right at the end, if you don't mind. Please stop me if my slides are not working or if you can't hear my voice. Otherwise, I would request you to have your questions until then. I'm not going anywhere. I'll answer all the questions. So let's begin. By the way, I assume that I'm giving these talks to mostly to scientific students. I also assume that there will be biologists or chemists in the audience. But let me tell you that the topic is so complicated that even for a physics student, even for a physics PhD scholar, this might seem a little difficult. Okay, so if you're finding it difficult, don't worry. Just have patience with me, and I promise you that by the time you go home, I'll give you a take-home message. And for physics students, I'm going to introduce you to some of the difficult concepts in physics. And well, this is not a lecture, so you're not going to understand everything, but at least you'll see how we think about these topics in the modern day physics. Okay. I call my topic inflation, quantum fluctuations, and primordial black holes. And this order that I have chosen has a particular reason, that I have to first explain you what is inflation, then I have to explain you what are quantum fluctuations, and when I combine both of them, then it might happen that there will be formation of black holes, and we will call them primordial black holes. We're going to define all of this in more detail. So I have to introduce you to inflation, and just inflation could be 2 talks. So I have to condense all sorts of cosmology into first few slides. So please excuse me if I'm not talking about cosmology, basic cosmology in an elaborate way, but I'm going to talk about all the prerequisites that you need to know to understand stuff. So the main topic is actually about black holes and what we call primordial black holes. So what are black holes? For a physicist, a black hole is a geometry of space and time. In physics, space and time are not some mathematical concepts but they are real physical quantities which can bend, which can twist, which can be flattened also. And this has a geometry, like the surface of a, let's say, a football. You can press it around a little bit and change the curvature. Similarly, space and time has geometry. And we understand that black holes are the geometry around an extremely dense central mass distribution. Okay, and there is a presence of a horizon for an outside observer. And these two statements which I made are extremely technical, but luckily we don't need to use them. So for us, a black hole is a very dense spherical object. Okay, so we have a sphere. Think of a planet or a star, a big sphere, and you just compress the sphere without changing its mass and compress it to a really, really small size. Okay, so it's a very dense spherical object. This object may be rotating also, or maybe not non-rotating. It doesn't matter. That is what we are going to call a black hole. So it's an extremely dense object. In fact, it's the densest object in the world. Okay. And these objects, these dense spheres, have been we have observed them. Like really observed. These are not mathematical concepts. We have observed them in nature. I'll give you just an example. Take our sun and just compress it to about 3 kilometers radius. Okay, our sun is really big. I just compress it to 3 kilometer radius, and that will be a black hole, that dense object. Okay. Here is a black hole's image, which they call image of a black hole, which they have taken using radio waves last year. It was a big news, and you must have, if you follow astrophysics or cosmology, you would have seen this image everywhere on newspaper or on WhatsApp status of people. This is not really the image of a black hole. This image is really what we are looking at is light coming from the objects which are rotating around the black hole, especially gas and all sorts of stuff. Okay. There's a huge black hole at the center that we call supermassive black hole. This is really huge. This is about 1 billion times massive compared to our sun. Okay, it's really a giant, and there's some gas rotating around it, and they have pictured the gas around it in radio waves. Then we also know that our galaxy, the Milky Way galaxy, also hosts a supermassive black hole at the center. This is about 1 million times as massive as our sun. So this is a very interesting topic, and one could talk about it forever, but I'm just saying that there are such objects. They have been observationally verified. And how do we know that this object is there inside? Because we have seen stars rotating around it. Okay. And when stars rotate around a very extreme dense gravitational object, they have very elliptic orbits around it. And by measuring the orbit of stars for 20-30 years, we know what kind of giant is sitting at the center. And this giant has a huge mass, 1 million times mass of our sun, and it has a very small size. And so from there, we know it has to be a black hole. Okay. By the way, a black hole is so dense, such high gravity that even light cannot escape. So if you shine a torchlight directly radially onto the black hole, the light will just go inside the black hole and not reflect back. So it looks black. That's why a black hole. Great. So we have several evidences for these black holes existing in our universe. They could be of stellar mass. By stellar mass, you think mass of a star. Okay. The mass of the black hole is similar to mass of a star. They could be supermassive, from millions to billions times the mass of a star. They could also be at the centers of giant radio galaxies and at the centers of active galactic nuclei. These are galaxies whose center hosts a powerful black hole as well as some gas around it, which is rotating around the black hole and getting heated up. These are very extreme powerful engines in our universe, gravitational engines. Then we have also seen black holes from gravitational waves. So if there are two black holes of some mass, they're rotating around each other. As they rotate around each other, they lose some energy due to emission of gravitational waves. So as they lose energy, they come closer and they rotate even faster, and they lose energy even faster, and finally they merge together. So we have seen this merging event and the gravitational waves from it since 2016. This is super hot topic in physics. And so we know that in the universe, there are black holes ranging from 5 times mass of our sun all the way to more than 1 billion times mass of our sun. Okay. By the way, mass of our sun is about 10 to the power 30 grams, 10 to the power 30 kilograms. Okay, it's a huge. It's about 1,000,000 times more massive than our Earth. And the question is, if there are all these black holes, how are they formed in the universe? Why are they there in the universe? They must have formed by some event. And we already knew that how they could form. In fact, studying how stars would die, big stars, we knew that black holes would exist. So this was a theoretical prediction. And then we observed that, yes, there are these black holes. So their formation is usually attributed to collapse of extremely massive stars. So if you have a huge star, and once it burns out all its fuel, there is nothing to stop the gravity to collapse the full star onto itself. So the core of the star will collapse and form a black hole. For that, for the core to be massive enough to collapse on itself, it has to have a mass which is greater than mass of our sun. Okay, the real number is not 1 here. It's sort of like 2.5. But the order of 1. Okay, so a black hole formed because of collapse of a star has to have a minimum mass of our sun. Okay, so I'm going to call it solar mass. So the minimum mass of an astrophysical black hole is solar mass. These black holes, we are going to call them as astrophysical black holes. They are formed by collapse of stars. Okay, they require existence of huge stars so that they have a massive core and then that can collapse. And since they require stars to be there in the universe, they form as late as 1,000,000 years or even later. So if there is a beginning of our universe, then you have to wait for 1,000,000 years for the first stars to form. And then these stars, they will burn out their fuel and the core will collapse. And finally, you're going to see a black hole. Okay, so you have to wait for 1,000,000 years. The question is, why do we have to wait for 1,000,000 years for a black hole to form? Can black holes form even early in the universe? Well, the answer is yes, and that's the topic of today's talk. I'm not sure how much I can progress given the time, but let's see. The topic is primordial black holes. We're going to call it in a cool way as black holes from the Big Bang. This is not a misnomer, by the way. This is a technically correct word. I'll explain it why. But it is usually thought that, okay, this just sounds cool and this may not be black holes from the Big Bang, but it actually is. Primordial black hole formation takes place early in the universe. Our universe today is filled with a lot of dark matter, a lot of dark energy, some amount of light, okay, photons, light, and some amount of neutrinos. But early times, if you go back early, when the age of our universe, by the way, today the age of our universe is sort of like 13.8 billion years. Okay, so 13.8 followed by 9 zeros. However, if you go back to a time when universe was less than about few thousand years old, at that time universe had mostly photons, a lot of photons and a lot of neutrinos, and less amount of dark matter and dark energy. Okay. So we are going to call primordial black holes are those black holes which are formed in the universe when universe was radiation dominated. By radiation, I mean light. Okay, so it has a lot of light. Okay. So the age of the universe was less than 1 second. So they formed that early. We don't have to wait for 1,000,000 years. I'm going to show you how they can form. This is just like gravitational waves, which I told you a super hot topic. This is also a very vast, very old, and a very hot topic. Primordial black holes. They keep coming back to physics again and again because they are very interesting. Okay, and this involves work which is both theoretical and observational. This is for physics students. If you want to know a research topic in physics, here is one. You can see that every day. In fact, I wrote every week, but you can check every day in archive, and you will see a paper on primordial black holes. Okay, so and it involves a lot of knowledge of physics. Okay, it involves knowing Einstein's theory of relativity. It involves basic concepts of cosmology. It involves bending of light. It involves quantum field theory in curved space-time. It involves gravitational collapse of objects, which we will talk. It also involves how structure formed in our universe. Okay, why do we have galaxies and stars and planets in our universe? Were they always there or they formed at a particular time? We're going to discuss. For people who are not physicists, don't worry about this slide. Okay, this is mostly for physicists. So let's first start with Big Bang. If primordial black holes are black holes from Big Bang, let's start from Big Bang. Here is a rough summary of how our viewpoint of the universe has changed. Okay, go back to a time before Copernicus and Galileo. We had a geocentric view where Earth was at the center, but that was thrown away and replaced by this heliocentric view where Sun is at the center. And this heliocentric view sort of stayed for a long time, even when William Herschel made a map of all the stars in our galaxy, and he put Sun at the center. Okay, so he was still thinking heliocentric. But then people figured out, no, we are not at the center. If this is our galaxy, suppose this is not our galaxy, some other galaxy, but suppose it is our galaxy, then we are roughly some distance away from the center. So we are just a teeny tiny star. There are about 100 billion stars in our galaxy, and we are just one star somewhere in the corner. Okay. And then when people looked at the sky in more detail in a telescope, then they see not only our galaxy, but thousands and thousands of galaxies. Okay. In fact, only in 1 degree angle in the sky, if you look at a patch which is as roughly as angular size as our moon, you're going to see about 10,000 galaxies. Okay. And our universe that we can see, as far as we can see within our horizon, we see sort of about 100 billion galaxies. Okay, so universe is an island of galaxies. Okay, so our view has changed from Earth being the center of creation to we are just some small planet around a small star in some random galaxy in the universe. So our universe looks like this. This was taken by Hubble telescope in 2003. And if this is just 1 degree, but if I increase the angular size of my telescope and look at suppose I'm a bird, I'm a big bird, and I can have a bird eye view of the whole universe, sort of, then it's going to look like this net structure, this spider web structure. We call it the cosmic web. Okay, it's like a spider web. Each dot here is a galaxy. Okay, and each bright, these lines, you see some filaments going on. These are some groups and clusters of galaxies and superclusters of galaxies. Okay, and you also see some void here. There are places where there is not much matter. Okay, that's also interesting. We'll discuss about it a little bit, but this is how our universe looks. This is not a real photograph, by the way. It's from computer simulation. So this is how our universe looks today. The question is, did our universe look the same way like it looks today all the time in past? Is it eternally static and not changing at all? How do we know? The answer is we can know it. And this theory, which says that the universe actually has been evolving, is a well-tested scientific theory. It's not an idea of some crazy scientist, or it's not a proposal. It's a well-tested, 100% guaranteed scientific theory, and we call it. The word is a misnomer, but anyway, we call it Big Bang theory. So we're going to discuss that a little bit. So before that, we have to understand gravity. Why? We're looking at the whole universe, like there are all these galaxies and stuff. All these galaxies, the net electric charge is 0. So they're not pulling each other or pushing each other by electric charge or any other force. The real force by which they are governed is really gravity. On that long length scale, large length scales, it's gravity which wins. No other force is that important. So we have to understand what is gravity. Now, gravity started from Newton's theory. Newton said gravity is a attractive force and which arises because of mass. So if you have mass and there is another mass, these two masses will attract each other by gravity. That was Newton's theory. So mass is the source of gravity and it is an attractive force. But Newton's gravity was quite successful. It still is successful for planetary science and sending rockets and stuff. But it broke down if you go very close to our sun, Newton's theory will not work. Similarly, if you go near a black hole or our whole universe on big scales, Newton's theory doesn't work. So we have to use Einstein's theory of gravity, which says the source of gravity is not necessarily just mass, but rather any form of energy. So energy can come from momentum, energy can come from mass, from viscosity, elasticity, all this stuff. So if any substance has 0 mass, for example, photons, which have 0 mass, they can still gravitate. Okay? The first difference from Newton's theory. Second thing is Newton said it's an attractive force. In Einstein's theory, gravity is not really a force. It's really bending of space-time, which I talked about before. Okay, so if there is gravity somewhere, it means space-time is bent in some way. If there is no gravity, it's a flat space-time. Okay. You can roughly think of this curvature of space-time, which you can probably imagine. You can think of roughly as distance between 2 points. So what gravity does is changes the distance between 2 points. You know the distance between 2 points is given by your good old Pythagoras theorem. But Einstein's theory says, well, that's not always correct. If I put a mass nearby 2 points, the formula for distance between 2 points is going to change depending on what kind of mass I put. This is Einstein's theory. And in this theory, this gravity, which you think of usually in Newton's way as attractive force, it could be attractive, it could be repulsive, both. First difference, okay? So gravity could be repulsive. Second thing, it could be sourced by massless objects as long as they have energy. So for example, light can have gravity. A black hole is a particular structure of space-time. So the structure of space-time is decided by what you put there, what kind of energy you put there. Do you put a rock? Do you put some light? Put a copper wire? What do you put? So black hole is when you put a very dense object, then the geometry of space-time becomes very twisted and very interesting. I will not discuss it today. That's a black hole. Okay? And you can think of a black hole as a solid sphere with a size or a radius given by 2 times g by c square into mass of this object. Okay? G is the Newton's gravitational constant and c is the speed of light. Okay. There's another example of this structure of space-time in Einstein's theory of gravity. So the first example I told you, a black hole, you put a dense spherical object and you study how the space-time or distance between 2 points changes. Or what you can do is you don't put a dense object somewhere. You take whatever mass or energy you have, you distribute it uniformly, okay, like a uniform fluid or a uniform gas, distributed. If you do that, then the structure of space-time is very different from a black hole space-time. In fact, what will happen is the distance between 2 points would still be like your Pythagoras theorem. You see here, this is the distance between 2 points is given by almost like Pythagoras theorem, delta x square plus delta y square plus delta z square. But there is an extra time dependent factor sitting there. Now we are going to call it the scale factor. Okay. So the distance between 2 points is not a static formula. It's going to change with time. So it may increase, it may decrease. So if I have a universe where I have put galaxies and all sorts of gas and photons everywhere, the universe cannot remain static. Either it's going to contract or it's going to expand or it's going to oscillate or do all sorts of stuff. Okay. This is what Einstein's theory says. We'll come back to the scale factor. But for physics students, so mathematically, Newton's theory is represented by a gravitational potential whose double derivative with respect to space is given by the density, mass density. So depending on how much mass density you have, that creates gravity. And the force, the field strength is really the derivative of this potential. Okay, you solve this equation and find finally the field. Now, if you know this gravitational field created by some kind of matter, you can figure out how objects move in this field. So if I put a small object in this field, how it's going to move is really given by Newton's second law, F equal to ma. Okay. In Einstein's theory, the situation changes, but quite parallel. Your equation, if I give you some mass distribution, you used to get gravitational field in Newton's theory. Here, I'll give you not just mass distribution, but energy momentum distribution. So I'll give you energy, I'll give you momentum, elasticity, viscosity, everything. You put here and you figure out how the distance between 2 points in space-time change. That is captured here. Okay. Whatever is phi doing here, g mu nu is doing here. That's basically the distance between 2 points. And then the field strength is one derivative of this g mu nu, just like here. Okay. And finally, how charges will. By the way, here by charge I don't mean electric charge here. By charges here I mean any point mass or a photon or something. Okay. This is gravitational charge basically. So how they would move if I have this kind of field strength here is given by acceleration equals to some kind of force. Very similar to Newtonian way, an analogy. Okay, but the equations are different now. Anyway, so let's go to cosmology. In cosmology, we have matter distributed uniformly everywhere, and Einstein's theory will say that the distance between 2 points cannot remain constant. It has to change with time. Now we want to know how it changes with time. Just a notation for physics students. I'm going to put speed of light as 1 and Planck constant as 1. And I'm going to put Newton's gravitational constant into a new variable which is called m Planck square. We're going to call it Planck mass. Okay, so just have it in mind. It's not very important. So the history of our universe. I'm going to write it down in one single figure, but this took about 50 years to figure out from a lot of combination of observation and theory. What we know today is that the scale factor, this distance between 2 points, any 2 points in our universe on large scales, has been increasing with time since 13.8 billion years. So since 13.8 billion years, if I had taken any 2 points in the universe, they have been increasing. Okay, and the way they're increasing is initially they were increasing in a decelerated manner, and in the present time it is increasing in an accelerated manner. So if I go to early universe and take 2 points, they will be going away from each other slowly, and slow down, and suddenly they will start going away fast. Okay, that's how our universe has been expanding, and this has a profound consequence. The consequence is the following: if our universe is expanding, it's not static. Then in past, if I take 2 points today, which have some distance today, if I go to past, these 2 points will be closer and closer and closer. If I go even to past, they will be even closer. If I go even past, it will be even closer. So you can calculate that how much time back you have to go so that all these galaxies and stuff that you see would be on top of each other, making universe extremely dense and hot. Okay, you can calculate it. And people did calculate it in 1940s. You get 2 things. First thing you get, if you keep going back, okay, just go back in time, close your eye and calculate. What you're going to hit is all the things in the universe are going to be on top of each other in 1 point. Okay, so at that point, density is infinite, temperature is infinite, size is 0, curvature is infinite. That point is called a singularity. Okay, we call it a Big Bang singularity. And whenever that point happened, it happened in a finite time in past. So if today I say today is the age 13.8 billion years, then this point happened exactly at t equal to 0. So in a finite time in past, there was a singularity. This is what classical physics, if you extrapolate classically without thinking anything, will tell you. But we don't believe it. We know that Einstein's theory has to change early times. Ask me later in the question answer why should this be? But we don't trust the theory that early in time. Okay, there's something happens and we know Einstein's theory will change and this will not work. But however, we know for sure that in past it was hotter and denser. Okay, so if we go back enough in time, so if there was a singularity, we're going to call it time t equal to 0, and today is 13.8 billion years. Okay, this should be clear. If we go from time t equal to 0 and then we go forward in time until about 3,80,000 years. Okay, by that time the temperature was so hot that electrons cannot rotate around protons. So electrons will go away from protons. Okay, since electrons will go away from protons, universe will be in a plasma state. So there are free electrons moving around, there are protons hanging around, there is light, there are neutrinos, there are all sorts of particles. So universe is like a soup. So this beautiful universe night sky that you see today, you just look up to the sky and you see stars. Or maybe you look in telescope, you see galaxies. You will not see that in early universe. Suppose you can exist in that hot temperature. By the way, this temperature was higher than 3,000 degrees Celsius. Okay, quite hot. But suppose you can survive there. You try to look far away. It's all foggy. Okay, it's a plasma, it's a soup. You can't see far away. But since universe was expanding, it was cooling down. Anything which expands, that cools down. Okay, so the temperature was going down. Eventually, we will reach a time when the temperature is low enough so that now electrons could move around protons. Okay, there is no energetic photons which is kicking it out. Okay, so it can now move around protons. Then what you form are neutral atoms. And neutral atoms, especially what you form in the universe, our universe, are actually hydrogen and helium atoms, okay, mostly. And we know neutral gases are transparent to light. You can see me through my camera, even though there is oxygen, nitrogen, everything here, because light just passes through them and doesn't interact much, right? So then universe first time became transparent. Before that it was opaque. like a soup. So when it became transparent, this light, which was always getting trapped, it was a foggy medium, now opened up. So this light could travel now. So this light started traveling everywhere in the universe. So you can see this light. Since universe is all there is nothing outside. This first time light got free. You can see it today. So that was a prediction of this theory, this so-called Big Bang. Let's call it hypothesis for now. I'll show you why it is a theory, a tested theory. So if this is true, then what I should see is that afterglow radiation, it should be a black body radiation. So it should fit whatever I see. If I measure the temperature of this photon, which will come to me today from the early times, what I should see is that it has a same temperature everywhere. It's coming from the universe, and it has a black body distribution. That means if I measure it in different wavelengths, red color, green color, yellow color, infrared, whatever, I should see a particular pattern of number of photons. Okay? So the number of photons should be higher in one frequency, and then it should go down at higher and lower frequencies. This solid black curve is actually the prediction of the theory. And you see these dots here. These dots are the observational data points. Okay, we observe it in camera and we see it. These are, by the way, when I say camera, these are microwave cameras. These are really antenna. You see the kind of match. Okay, and the most interesting thing is these data points also show you the error in the observation. Okay? How much is the error? So there are these vertical lines which are error. The errors are so small actually that you can't even see it. So just to show you that there is error, what people have plotted here is increasing that error by 400 times. So each line here, vertical line, should be reduced actually by 400 times. So that kind of match with the prediction. Okay, this is the first. So this first time opened up that we can know the origin of our universe sitting today in our home. Okay, and this was, you can imagine what kind of impact it would have at that time, when people would still think of mythological creation stories. Okay. And now we know that, oh, our universe was really a hot and dense soup when it was less than 380,000 years old. But today it's not. It has galaxies and all beautiful things. Okay. So this light was seen. Another prediction was this light should have same temperature everywhere in the sky. Why? Because as long as temperature was hot enough, universe was soup. As long as temperature was low enough, cold enough, photons could travel. So there is a particular temperature where this transition happens, and its temperature is the same. It doesn't depend on which point it happens. So wherever this light is coming from, it has the same temperature. Okay, so let's go and look at the sky. Let's take a camera which can measure, a thermometer which can measure this temperature, and just look at the sky in all directions and see if we are seeing the same temperature and same black body distribution or not. And people did it, and they saw it. This color here basically says temperature. Okay, if the color is same color, it's same temperature. So we saw same temperature all across the sky. Anyone who is confused by this elliptic nature of sky, I mean, you must have seen geography maps, right? When you project Earth, which is a sphere, on a flat paper, you put this elliptic maps, okay, where this point and this point are the same points. Similarly, we have looked at the universe from Earth in every direction, and we're done. Okay, so this is great. This is the first success of this model, and they said that this became a theory now, of tested theory, that our universe was actually hot and dense. But there was a problem. The problem is, if it was so smooth, everywhere the same temperature, great. So it was hot and dense soup and same temperature everywhere. Then it cooled down to form hydrogen and helium. And this hydrogen and helium should have same density everywhere in the universe. Small, tiny fluctuations in the universe. You can think of them as temperature fluctuation or density fluctuation. They're all similar. So there were these fluctuations, and they are key to our existence today. So we would like to understand why there were these fluctuations. Why wasn't it completely smooth? Or why wasn't it completely chaotic? Why it's almost smooth, but still there's this fifth decimal place fluctuations. Okay, so this I want to discuss now. This is a rough timeline of the history of our universe. Our present universe, which is 13.8 billion years old, has a lot of galaxies and stars and planets. But if you go back to a time when universe was 100 million years old, then the first stars were being formed at that time. If you go back to 380,000 years, the first atoms formed, which I talked about. Before that, it was so hot that everything was a plasma. Then if you go back to a time when it was 60,000 years old or before, universe had mostly photons and neutrinos. Okay, it was mostly light, okay, very less dark matter and normal matter. And then if you go back to 3 minutes or before, you don't even see nucleus. You don't see there are no nucleus, just quark gluon plasma kind of stuff. Okay. And if you go back much before, there is a period which is called cosmic inflation, which I'm going to touch now. This cosmic inflation, which is a very interesting process, this happened when universe was less than 1 second old. You see that a universe which is 13.8 billion years and we are living today, we are talking about time when it was less than 1 second old, and we can make a prediction and actually test it. That's the power of science today. Modern physics, that we can test all these things and really know how universe was created. Okay, so let's talk about this a little bit. I'll skip this. So here is another timeline. So there was something which happened in the beginning which we don't know. Then we know that there was a small period of accelerated expansion of space. Space has been mostly expanding in a decelerated way. For our universe has been expanding in a decelerated way, slowing down for most of its history, right until today. Today it's expanding acceleratedly because of something called dark energy, which I'm not talking about. But right in the beginning, there was a fraction of a second when universe actually accelerated. It was a transient phase. Okay, for a fraction of a second, it accelerated and then started expanding in a decelerated way. This place where it accelerated like boomed up, we call it an inflation, cosmic inflation. Okay? It inflated, and within a fraction of a second, universe inflated by about 10 to the power 25 times. Okay, so this is really 10 to the power 25 is roughly like e to the power 60. We call it 60 e-folds. So universe expanded by e to the power 60 times within a fraction of a second. So you can imagine what kind of inflation it was. And then it had nucleus formation. Then slowly it had this soup where you had nucleus and electrons moving away from each other. And then what happened? Universe, the first atoms were formed and the first light started propagating. This is the light we have detected as a black body radiation. There has been 2 Nobel Prizes on this particular part in physics. And then slowly these fluctuations would grow because of gravity. Wherever there was a high density, that will grow to form structure. So then slowly we have galaxies and clusters and stuff. This is the story. Okay. So what happened in our universe? So we had a transition from a plasma phase to a cold gas phase. Okay. So initially it was a plasma, then became a gas. If we don't have any fluctuations initially, universe was perfectly smooth. Then it will be filled with dilute hydrogen and helium gas today. We'll have no structure. But if we have teeny tiny fluctuations in the universe, then today we'll have galaxies and stars and planets. So these fluctuations are very important. And these fluctuations are very small. The density fluctuation from one place to another place, the density difference, divided by whatever is the density, average density, its square is about 10 to the power minus 9, so very small. Okay. And what is the origin of this density? I want to show this diagram. I always show it in my talks. These fluctuations have been measured by better and better angular resolution. Okay. Initially, there was a satellite called Kobe, which went in 1990, and it saw these big spots in sky, some 1 degree, 2 degree spots in sky. And you see that if you go from this spot to that spot, temperature changes a little bit. Then there was WMAP, which measured it up to even smaller angular scale, and you saw some more pattern here. Then Planck satellite, which is the recent state of the art, has actually nailed it down completely. And you see spots whose size is all the way from 90 degrees to about 1 arc minute, very small. All sorts of fluctuations are present. Okay. And how they grew is that if you start the universe and you put a lot of particles and you start with tiny fluctuations. You look this diagram, it's like an early universe, and it has all these atoms, hydrogen and helium atoms, and they're almost homogeneous and isotropic. Okay, they look almost same everywhere. It's very tiny, somewhere a little higher, somewhere a little lower. If you leave them under gravity, what will happen is the higher density parts will start to become even higher, and the lower density part will become even lower. And from here to here, it becomes more clumpy, then it becomes more clumpy, and finally today it is very clumpy, and it has this spider web kind of structure with filaments and stuff. So you can actually generate this. If you put everything, you put photons and electrons and atoms and dark matter, dark energy, you can just do it. So it's a very well tested theory of our universe. We know this is how our universe was, structure was formed in our universe. But since these fluctuations in density were very small early times, so gravity has to take a lot of time to compress them and finally form a galaxy. So it takes about 1,000,000 years, or even a little more, 100 million years for a galaxy to form. It takes few million years for stars to form. So it takes a really long time for this structure to form. And since we said black holes form by collapse of stars, since star formation takes million years, black hole formation takes 1,000,000 years. That's why black holes are formed late in the universe. These are the story of astrophysical black holes. The question is, these fluctuations which we have measured, the spot sizes, they are from 90-degree spots to 1 arc-minute spots, and the temperature difference is very small, 10 to the power minus 5 between any 2 points in the sky. What if I go below 1 arc-minute? I go from 1 arc-minute to 10 to the power minus 10 arc-minutes. If I had a camera which can resolve this small angle, is it guaranteed that these fluctuations were smaller? That's the question. Answer is, it is not guaranteed. Okay? And we have to go to the origin of, to understand this, we have to go to what created these fluctuations. And the answer is this cosmic inflation. This initially, before 1 second, there's a fraction of a second where universe expanded exponentially faster. Okay? That cosmic inflation during quantum mechanics of acting during this small time and energetic process actually created these fluctuations. I'm going to sketch you how it is. I'm not going to explain you in detail because I'm running out of time. This cosmic inflation explains why these fluctuations are there, but it also explains a lot of other things which I don't have time to talk about today. It explains all this hot Big Bang model which I told you. Universe started as a soup and became a structured universe. This is so well tested, but it has some unnatural initial conditions. It works if initially I do some abracadabra. Okay, I make the universe almost smooth. Okay, the temperature is almost same, very, very small differences. Then I make the universe almost flat. In the sense, if I take a big triangle in the universe and add up the 3 angles, it's going to be about 180 degrees. So it's like a Euclidean space. Okay, but Einstein's theory says it could be Euclidean, it could not be Euclidean. In fact, in an expanding universe, even if you start with almost Euclidean, as time goes on, it becomes more and more curved, either positively or negatively. That's another problem. Then we also predict from some fundamental physics that there should be magnetic monopoles in our universe. There should be some cosmic strings, some defects, but we don't see them. Okay? And there is an age-old big problem in physics, why our universe is big and old. Why didn't our universe expand just for a while and then compress and collapse? What made it keep expanding for so long? Okay. These are all very interesting questions, and these are very unnatural. Unless you say, okay, before this soup phase, I had this inflation phase where universe was expanding very fast. Then it solves all these problems. It doesn't fully solve this last one, but it addresses this. So we need this period of rapid accelerated expansion. I'm not going to tell you how it solves these problems. Okay, I don't have time for that today, but I'm going to tell you how inflation solves the problem of creating these fluctuations, tiny fluctuations, in a sketchy way. So what we need universe to accelerate. Nothing, universe has gravity, right? So suppose initially something happened because of which it has some speed, but the speed should slow down, right? Because everything is attracting each other, so it should slow down. Why is it accelerating? Today it's accelerating. It also accelerated for a small fraction of time in the early universe. I told you that Einstein's theory can be both attractive and repulsive. If you put repulsive gravity matter, it can be repulsive. So if I want a universe to acceleratedly expand in the early times, I need some kind of a repulsive gravity matter. I need some matter which acted like a repulsive gravity for a tiny fraction of time. Do we have any such matter? Answer is yes. The matter is called inflaton, which I'm going to talk, and this expansion it caused, the accelerated expansion, is cosmic inflation. Okay, and this makes all this unnatural abracadabra as a natural prediction. No matter what you do, this should happen. This is very interesting. It's a different topic. We'll talk someday. Okay, so I have a detailed slide of how exactly inflation happens and quantum fluctuation happens. But looking at the audience, the mixed audience, I'm going to skip it. I want to come back to it if physics students are interested sometime later. Okay. I had put really interesting slides here, but I don't think it'll be too much. All you have to imagine is that our universe has some kind of a field. Okay. This field is everywhere in the universe. Early times, there is nothing. There is no photon, no electrons, no matter, nothing. It's an empty universe. In terms of particles, there are no particles, but there is some kind of energy which is filling the universe. Okay? And this energy is given by a kinetic term and a potential term. So there is something which is moving and it has a height. Okay? The combination of kinetic and potential term is actually giving rise to inflation. This is the energy which is filling the universe. Okay. Great. So there is some kind of, there is this field which is everywhere in the universe, and this field is rolling down and down and down. Okay, as long as the field is moving slowly, it has its kinetic energy. It's smaller than this height, this potential energy. It causes the universe to it behaves like a repulsive gravity substance, and it causes the universe to expand exponentially. But as time passes, it slows and it speeds up and speeds up. And then there is a time when the kinetic energy is higher than the height. Okay? Then it cannot act like a repulsive gravity. It acts like the normal attractive gravity. Then what happens? This field has some energy. It oscillates here, right? It's just common sense. Right? It will just come from here and like this and then oscillate. As it starts oscillating here, it will lose quantum mechanically its energy. So it will produce all the particles that you see today. All the electrons and all the quarks and all these things were formed during this process. So early times universe had no particles. It had this energy which is filling the universe. It was repulsive gravity. And then finally the energy got dumped into normal particles. That's the story of inflation. But this is classical motion. Classical physics says it moves like this. Quantum physics says that as it moves, it sort of fluctuates like that. Up and down everywhere. So overall, as the field rolls down, there is some fluctuation in the energy density of the universe. So when this inflation is over and this field dumps its energy into normal particles, these produced particles will also have some energy density fluctuation in them because of quantum mechanics. I had all those previous slides to explain how this happens, but take it for granted for now. Okay. And what we observe from this satellites, I told you, Kobe and Planck, all these satellites, we observe from 90° to 1 arc minute. Okay, that observation is only this part of the fluctuation. So when it fluctuates here, this is what you see. From there all the way till it ends, the process ends, we are not able to see because it's in a small angular scale. You cannot resolve it. So there's a lot of physics going on here. We don't know how it looks. All we know is this part looks like a flat. This part looks like a plane. Okay. What can happen is that this part could still look like almost flat, but in the center part, there could be a very flat region, what we call an inflection point. Okay, such a point is called an inflection point. So the potential was going down, then it became sort of like an inflection point, and again went down. Here, the field actually slows down. If it is stiff, it rolls faster. If it is flat, it rolls slower. So it slows down. And it turns out these fluctuations which quantum mechanics produces, these density fluctuations, are actually inversely proportional to the speed. So slower is the speed, higher is the fluctuation. So what can happen is as the inflaton field slows down, it creates a lot of fluctuations. So it's not 10 to the power minus 5 now. It's probably 10 to the power minus 1 or 10 to the power minus 2. Okay, that's quite high fluctuation. Okay. So what will happen if I have those high fluctuations? Sorry, I'll skip this slide. I'm sorry. So what would happen if you have these high in the normal sense, in the normal scenario of inflation, if there is no inflection point here, then you have some 10 to the power minus 5 fluctuation on this 90° to 1 arc minute sky. And as you come to smaller scales, you have even smaller and smaller fluctuations. Here I'm plotting the amplitude of fluctuations, and this is like the angle. Think of it at angle. Okay, this is large angle, this is small angle. So at small angle, you have small fluctuations. But if you have this kind of a feature, what it does is it amplifies the power at small angle. So at large angle, you have some power, which is 10 to the power minus whatever. And then it was going down, but suddenly as it slows down here, the power booms up. What I'm calling is power is really the fluctuation amplitude. Okay, it makes it really fluctuated. So you see the power, it goes up to 10 to the power minus 2 or 10 to the power minus 1. So you have large temperature and density fluctuations on small scales. This is what is the take home message. This can happen. Okay. So this is how physicists look at small scale physics, early universe physics, small scale fluctuations. You can know what kind of potential energy was there in the universe if you can find large fluctuations at small scales. The question is, can you find large fluctuations at small scales? What is the physical outcome of it? If we have large fluctuations, so what? Okay. So what will happen is the following. Think of this as a large angle. Think of angle decreasing like this. Okay, from here to here. This is a difficult diagram, but it will help us. Angle is decreasing like this. This is during this is where inflation ended. Right of it is normal hot Big Bang universe, the soup universe, and left of it is the accelerating, early times accelerating, only energy filled universe, okay, which we call inflation. Now the fluctuations which are produced on large angles, they are small fluctuations, and these fluctuations take a long time to grow and form stars and then black holes. But the fluctuations on the small scale can be large. If they can be large, they will grow very soon, and they might form black holes directly in the early universe. So what would happen? We have a soup universe. On large scales, the universe is expanding. On small scales, it will keep collapsing and form all these black holes. We don't have atoms, we don't have stars, we just have soup. And the soup collapses at small scales and keep forming black holes. And these are the primordial black holes that can be formed. Okay, this is a difficult topic. I will skip it, and in last 3 minutes, I'm going to talk what are primordial black holes. This I talked about how they can be formed. It can be formed by having large quantum fluctuations on small angular scales in the sky. But if you don't understand this, no problem. We're going to discuss what are primordial black holes. Okay, I'll skip some of my work, and I'll go to I'll go to things which will be relevant for everyone. Now, this topic which I talked about for this slide is for physics students. This could be approached from very different angles. First thing is this topic can be used to study small-scale primordial physics. By primordial physics, I mean early universe physics. This is the physics of the universe when universe was less than 1 second old. Okay, so we are trying to really study really early universe. Okay. Second thing, I could have given a talk where I could have just talked about primordial black holes. Okay, I'm going to talk about it for 2 minutes, but and I would have highlighted why primordial black holes are so important. They're important for different things. Okay, I'll discuss in next slide. Or this could have also been a talk in studying this inflaton potential. What kind of features be there on this inflation potential? What kind of features we can find? Can we have these inflection points that I told you? Can we have some bumps, some dips? And depending on that, you will see some weird objects in the universe. You may see a very massive galaxy at early times. You may see a supermassive black hole at very high redshift. Or you may see a black hole even before atoms form, like I showed you. I talked about this primordial black holes. Okay. And then there are many other related topics. How exactly this soup collapses and forms black holes. Okay. Just keep these things in mind. Okay. Now coming back to some ground level stuff. So what are these primordial black holes? These are black holes which are formed by collapse of primordial soup in the early universe. These things, since they don't form from stars, they don't have to have a minimum mass of 1 solar mass. I told you astrophysical black holes have a minimum mass of 1 solar mass. These black holes don't. they could have as small mass as 10 to the power 15 gram. 10 to the power 15 gram is a mass of a mountain. Okay, so they could have Himalaya mass black hole, or they could have as high mass as 100,000 or even 10,000 solar mass, or even 1 million solar mass, also possible. Okay. Second thing, we know that our universe has dark matter. It's some kind of matter which doesn't much interact with light. It behaves like some kind of a massive substance. It expands our universe in a particular way. It turns out you don't need to introduce a new particle for dark matter. If these primordial black holes form in the early universe by collapse of this plasma soup, then they can actually explain dark matter in our universe. So it's a very economical way, and they are one of the primordial black holes are one of the important candidates for dark matter. They can also explain the origin of LIGO binaries. So LIGO is gravitational wave observatory, which is seeing all these binary black holes colliding. The question is, how are these binary black holes formed? Their formation is quite complicated. You can astrophysically form them, it's complicated, or maybe they are just primordial black holes. Two primordial black holes found themselves and rotating around each other. Okay. Then they can also explain why we have these supermassive black holes at the center of galaxies. Maybe because there are some heavy primordial black holes in the early times, and they sort of merged together and grew to form. Each of these are very important and hot topics. Okay. The way I gave the talk from today's perspective, I was talking about probing the small scale primordial physics. Primordial black holes could also be interesting for the ninth planet. Okay, I'll talk about it. And they could also be important for testing Hawking radiation. So Stephen Hawking showed, and then many other people showed, that a black hole is not a perfect object. Okay, it's not a very beautiful spherical object. It actually radiates. So it's like a glow. It's not really hot. But it has a temperature. Okay? And the temperature that it has, this is also because of quantum mechanics. It will have a temperature, and the temperature is inversely proportional to the mass of the black hole. And in fact, if the black hole is solar mass, it has 10 to the power minus 7 Kelvin. That's a very small temperature. So, and if it has even higher mass, it has even lower temperature. So you cannot detect Hawking radiation. That's why Hawking died without getting a Nobel Prize. You can't test it. It's very difficult to test. But if there are primordial black holes, they can have as small mass as possible. So they can have as high Hawking temperature as possible. That's great. You can test Hawking radiation. Let me tell you what kind of size they have. If a primordial black hole is solar mass, it is 3 kilometers big. Okay? It's a sphere of 3 kilometer radius. If it is Earth mass, it is 1 centimeter. It's a tiny black hole. If it is lunar mass, it is 0.1 millimeter. If it is asteroid mass, it is micrometer, like a cell, okay, bacteria or something. Then if it is Himalaya mass, it is even as small as a nucleus, atomic nucleus. So this could be really tiny, moving around in the universe and making dark matter. So detecting them is a very interesting topic. We know that all the Neptunian objects, which are outside Neptune, are sort of aligned in a particular way. Their motion around Sun is aligned in a particular way. Now, all these unusual alignments could be explained if we say there is a ninth planet. I'm not counting Pluto, so usually there are 8 planets, but if there is a ninth planet whose mass is about 5 to 10 times Earth mass, then that planet can describe this kind of alignment. Okay, so people are searching. But since we are not finding it, maybe it's a black hole. It's a primordial black hole. It cannot be a normal black hole because a normal black hole has to be more massive than solar mass. And this black hole, this object has a mass, Earth mass. So it's smaller. So it could be a primordial black hole. I've given you a reference. You can hear a talk about this topic. And it could really be like 10 centimeter. Okay, it's like a scale. So the scale that you had in school. So it's really tiny. People are now planning to send probes to detect Hawking radiation from this black hole as radio waves. So Hawking radiation of such a black hole would be around 1 Kelvin. So which will be radio waves. So you can actually measure. Okay, I'll skip observational constraints and all the higher topics, and I'll go to conclusion. Okay, so primordial black holes are extremely interesting objects. because they are formed in the early universe from the plasma state, and they can explain a lot of astrophysical and cosmological processes. So they have important implications in physics. There has been a lot of theoretical as well as observational work people have been doing, and I have made some theoretical work on this topic. Observationally, this is an active field, and you have to detect, like I told you, the planet 9 may be a primordial black hole. Then the existence of these primordial black holes also give rise to two kinds of gravitational waves. One could be because of the binary primordial black holes merging. Other one could be just because of their existence, they fluctuate the metric of space-time, the distance between 2 points, they will fluctuate it. And that will travel as a gravitational wave, which I could not talk. Okay, this is the conclusion, and here is the take-home message. The take-home message is that our universe was a hot and dense plasma, early times. Today, it is an island of galaxies, and it really made a wonderful transition from this hot, dense plasma to today's universe. And we understand how exactly it made over the period of 13.8 billion years. But if there was no fluctuations initially, then we would not see the present-day universe as island of galaxies, but as just gas, hydrogen and helium gas. But the fact that we see it as structure, as galaxies, means there were some tiny fluctuations which were there. And these were tiny on large angular scales, from 90 degrees to 1 arc minute. But these fluctuations could really be large at small angular scales. And if they are, they would form primordial black holes early in the universe, when universe was less than 1 second old. Okay, and the mass of these black holes could vary from mountain mass to all the way to billion solar masses. So bottom line is that black holes are extremely interesting objects, both for fundamental understanding of laws of nature like Hawking radiation, what created quantum fluctuations, what is inflation and stuff, to astrophysical and cosmological things like dark matter, planet 9, LIGO binaries and stuff. And primordial black holes are, of course, even more interesting. Chandrasekhar thought of black holes as the most perfect, symmetric, beautiful objects, okay, in 1960s and 70s. But in the modern language, Stephen Hawking said that black holes have Hawking radiation. They are really chaotic objects. They have this glow coming up all the time. So this is how our view of black holes have changed. I'd like to stop here. Thank you.